Okay, I got 6:30 by my clock, so we'll go ahead and get started. Welcome everybody to our Advanced Storm Spotter talk tonight. My name's Alex Zwink. I'm joined with other meteorologists here at Norman, Philip Ware and Vivek Mahali, the Dr. Vivek Mahali. And we'll be giving you guys a talk kind of through some more advanced topics than our normal Storm Spotter courses, and kind of just kicking this off to kind of give you an overview of what to expect during this spotter talk. We're going to start off kind of as a reporting refresher. I'll be talking to you guys, kind of, pretty much a lot of the topics in the basic course kind of condensed down into just kind of a little bite-sized piece here at the beginning. Then we'll kick it over to Phil, where he'll talk to you guys about severe weather meteorology, and then Vivek will finish us off here with some storm structure and evolution. Just a little bit of kind of basic notes about the course and everything. First off, you don't need a microphone. Vivek, Phil, and I are going to be doing all the talking. You'll be able to hear the webinar through your computer speakers, or if you guys happen to be using the app, you'll hear it through your phone. So the training that we've developed for this is actually specifically for our forecast area, the western 2/3 of Oklahoma, as well as a little bit of western North Texas there. However, it's really, and a lot of this information includes, hazards that are specific to us here in Oklahoma and Texas. However, a lot of this can be also applied to elsewhere in the United States. Other places get tornadoes, get hail, get wind. And so pretty much it's applicable, but we definitely encourage, if you have any local spotter training that's offered by the local forecast office, we also encourage you to go to those as well. Is the webinar being recorded? That says no, it actually is. Will it be re-uploaded for later use? That I'm not 100% sure about. I'll be discussing that kind of with our administrators. I don't know why the slide went forward, but be discussing it with our administrators, see if we want to go ahead and do that. Likely will, given that this is the weather festival, just so that we can have it available. Which also, on that note, welcome. This is actually a part of the National Weather Festival. We've made it virtual because, unfortunately, how it usually is everybody would come to the National Weather Center in Norman, Oklahoma, and it's basically our big open house. Unfortunately, with the current global pandemic going on, we can't do that. And so we're doing a week long of events that, pretty much all the different entities are posting stuff online. And so with that, this is also being hosted as kind of a special spotter talk for that. I'd highly encourage, after you guys are done here, go check out all the additional content, a lot of different entities. I know Vivek also was on a panel for severe weather where they basically did a kind of a Q&A for people's questions. And then lastly, one other thing that's a big question is, will I get a certificate? Yes, if you complete the webinar, what we'll do is we'll email you a certificate of participation to the email address that you used to register. There's going to be a lot of you. Right now, there's about 230 of you. So pretty much we'll be going through and emailing each of you this. So give us a few days to get that, and it'll allow you to print it off and have that certificate for yourself. If you want to go ahead and ask a question during the webinar, we do have the ability to ask that using the GoToWebinar interface. Go ahead and enter in and submit it. A few of you guys have been talking to us about stuff that's going on kind of in your local area. You can send that to us, and either Phil, Vivek, or I will be answering the question. One additional thing that we would like is if you guys could go ahead and put the number of people you have watching the webinar within the question box for us, because it's just kind of a record keeping for us. We like to know, how many people are we actually reaching with these webinars. So, we would really appreciate it if you could put it into the question box there. One more thing, like I said, this is kind of just giving you the basics of what you need to do with storm spotter training. We definitely encourage, if you have a local emergency manager or spotter group leader, get in contact with them. just so you can kind of organize yourself and be a part of it, you know, help yourself integrate into a team to better effectively be able to spot these storms to really help us in these severe weather situations. And some groups are like, oh, great, you took the Weather Services online training. Well, you know, join right up. Some others might have some more rigorous guidelines to that. So definitely go check with local emergency manager or spotter groups to figure out, you know, if you want to participate, figure out what you need for that. With the GoToWebinar and unfortunately the internet, sometimes you might briefly lose audio during the webinar. It should come back fairly quickly. You know, not really much to be concerned about. If you are going to be tweeting out anything about this, we encourage you guys to use hashtag Skywarn. I would go in there and also add in an hashtag NF's National Weather Festival, so NWF 2020, considering this is part of the National Weather Festival. So, you know, just use those hashtags. Let us know what you guys are watching out there. So anyways, that should be enough for the basic introduction. Let's kind of get into a little bit about the basics of pretty much storm spotting. And really to lead it off, it's difficult. Whenever you have any sort of storm like this, there's so much for you guys to look at and to be able to identify. You know, hey, is the storm, do you see that you have the tilted updraft there? Do you see that the updraft in the storm is rotating? All the different components of the storm, like your forward flank downdraft, your shelf cloud, your heavy rain, hail, you know, so much of it to look at. And really on our end, you know, it's a little bit, you know, there's a lot of challenges that we also face as well. And so within that, at the forecast office, you know, we're sitting there watching the radar, kind of getting, you know, getting ourselves situated. And one of the big things is that we know that there's a storm there. We could see that storm on the radar, and we think it's producing or about to produce some severe weather. Which we can see, you know, by a storm intensifying there on radar. The big thing is, and this is kind of a common misconception, is we really don't know exactly what's going on at the surface. We think we do, but we don't 100% know what's going on. And so for you guys as spotters, what we really need is for you guys to tell us what's really happening. Do you see a lot of large hail there at the surface? Do you see a tornado on the ground? A lot of that's really important to be relayed back to us, because when we go into making a warning decision, a lot of it can be the difference between, hey, are we issuing a severe thunderstorm warning or are we issuing a tornado warning? Or if we're issuing a hail, you know, severe thunderstorm warning, should we basically put a considerable tag on the strength of the severe thunderstorm warning due to it being 2 inches or larger hail? There's a lot of that that's really, you know, critical to us. And whenever we issue a warning like that, we use basically what we call a preponderance of evidence. And so kind of the big important stuff at the top of the list of what we're looking at when we make a warning decision, one is radar data. Radar data is invaluable for us, but right there at number 2, you guys, we have spotter reports. People out in the field telling us, you know, hey, this is going on at the surface. So it's a very vital part of, you know, pretty much our warning decision process. Kind of going on down the list, you know, going into an event, knowing the environment ahead of time, knowing kind of, you know, it's like, okay, we know that we have a lot of storm relative helicity or the spin of the atmosphere ahead of these storms. So it's going to be moving into an environment where it might intensify any sort of rotation. Knowing conceptual models, understanding how storm theory works, and also the history of a storm. Because if a storm has already produced a tornado and let's say the tornado is lifted, we know that it's actually likely to produce another tornado on down the line. Further below that, forecaster intuition, forecaster experience, you know, repetition, watching these storms over and over again. You kind of get a good sense of how they interact, especially with geographic features. And then lastly, the one thing that we do actually consider sometimes is the potential storm impacts and the potential warning impacts. For example, issuing a tornado warning in Oklahoma City at 4 in the morning. Well, we can kind of cut in pieces of Oklahoma City out that are likely not going to get impacted, but you know, hey, we're still going to be deciding it. And really those kind of impacts and who we're waking up at 4 in the morning, especially compared to all the other kind of decision points, that's kind of there towards the bottom. And going back into kind of why it's important to have spotters, relaying this information back to us is kind of like what I mentioned. Hey, we have this storm here, we see it on radar, we can obviously tell that it's ramping up in severe, we can tell that there's a little bit of rotation in it. However, that rotation is kind of at a tipping point of, do we keep going with a severe thunderstorm warning? Do we go with a tornado warning? And in reality, kind of with the paradigm we're in now, and impact-based warnings, we have a wide variety of different kinds of tags and additional information we can provide in the warning. Like, for example, severe thunderstorm warning with elevated warning, or severe thunderstorm warning where the severe thunderstorm's very much rotating, maybe producing a wall cloud, a funnel cloud, where we might need to toss in a tornado possible. And then your various amounts of tornado warning tags of, you have radar indicated tornado versus an observed tornado. The observed tornado is, yes, there is a tornado on the ground, rather than we definitely see the rotation on the tornado warning, but we haven't actually had it confirmed at the ground. And again, I can't emphasize this enough. Whenever we have that verification and we can include it in the tornado warning, it gives it that much oomph of having people be able to, this tornado warning is the real deal going on. There should, you guys should take action as soon as you possibly can. And so really kind of that's the slide says, spotter reports really help drive the message. So background of why the spotters are really important to us. Let's get into a refresher on reporting these hazards to us. And so first things first, what makes a good report to the Weather Service? First, that it's timely. If you tell us 30 minutes later, oh yeah, that storm had rotation on it, not very useful to us. If within the next, as soon as you see it, whether or not minutes or even sometimes seconds, giving us a call, sending us in a spotter network report, any of that, telling us, hey, we have the storm going on and this is what it's doing, that's what really makes a good report. The report's concise, something short, sweet, to the point. Not necessarily a meandering thing where it's like you're explaining, pretty much your explanation takes a lot longer to digest than, basically just telling us, hey, we got quarter-size hail at this location. That right there is kind of a perfect report of what we're looking for. Another one is calm. I understand it's very exciting what's going on out there. It's helpful to be calm, so I'm not having to calm you on the other side of the phone being like, okay, hold on, let me make sure I got this right, But I mean, in general, I can understand you being excited, but really getting a concise, calm, quick report is very useful. One that's clear, being able to very clearly state, this is what I'm looking at, so we can get back to the warning process as fast as possible. And then accurate, which there's, whenever you're looking at a storm, you might mistake one thing for another. This happens a lot with identifying tornadoes, making sure you check your bases of, is the storm rotated? Is it connected to the base of the wall cloud? Kind of stuff like that. Just making sure that you are correct in what you're seeing is very good. And then objective. People love knowing that they've basically reported in a tornado. Make sure that it really is a tornado of what you're looking at. And so really kind of along with that, who are you? Give us your name, basically identify yourself. Where are you at? Where you are exactly at a location, easy to find on a map. Usually if you're like, I'm 3 miles west of Springer, Oklahoma, something really that kind of gives us a geo reference to a town, that's very good in our books. What do you see? Describe it, be brief. Where did you see it? Where the hazard was, not necessarily where you are. Hey, I'm 3 miles west of Springer. I'm looking east about a mile or two. There I saw possibly a funnel cloud reaching to the ground. And then also, when did it happen? Be specific. We can understand like if you are a couple minutes later than normal, but just kind of be as accurate as possible. That's really kind of the gist of what we're looking for with these slides. And so identifying yourself, if you're in our area, calling the forecast office saying you're a train spotter, storm chaser, just kind of real quick, hey, I'm a train spotter, storm chaser. We're not going to give you the 9th degree. We're going to be like, okay, and if you identify yourself as a train spotter or a storm chaser, then that kind of leads us to accept, kind of what you're saying that much quicker. If you're in another forecast office's area of responsibility, definitely get in contact with them just to be like, hey, I took this training from Forecast Office Norman. I just calling to just make sure that I'm doing this correctly if the time arises. Some offices use ID numbers, some kind of are like us, so just, hey, if you identify yourself, that's great. And then, of course, check with local emergency managers and spotter networks. Okay, and so how do you report, especially to us at the Forecast Office in Norman? Probably one of the best ones is 405-325-3816, our phone number. We're here 24/7, so even if it's 4 a.m. and you had a hailstorm move through, you go out, you measure it, you're like, yeah, that's some good golf balls. Call us. I highly encourage. We will always be happy to get a report. Next is spotternetwork.org. There's a little bit of a sign up that goes along with it, but this gets fed right to us and our internal chats. So we'll be able to see that right away, especially with your location and what the hazard was. Amateur radio, we still use ham radios that are pretty much right next to one of our computers that is always manned. So if you call in with anything, we're WX50UN, and we'd be happy to hear from you. Tagging us on Twitter, social media, especially Twitter, has been great for this. It's been very useful because it's something that we have somebody monitoring and somebody will see. So go ahead and tag us with that, and we'll probably give it a like right away and get an LSR made for that. We could also use imping. Imping actually gets fed into our data stream. So if you do an imping, it'll pop up right onto our overlays that we have. And so those are the really good places to send us reports. I would say probably if I were to order things, I would go phone number 1, Twitter number 2. Those two are something that we're usually always 100% monitoring, and you'll always get in touch with somebody to communicate, hey, this hazard's ongoing. Going on kind of a couple of ways that you can get in contact with us, but it's definitely not always monitored. One is sending us an email to our spotter email account there, sr-on.spotter@noaa.gov. It's very hit or miss whether or not somebody is paying attention to it. The other method would be Facebook at NWS Norman. I'd highly encourage, if you want, you can post pictures and tag us in it. But just unfortunately, kind of with how Facebook works, it's kind of hard to keep track, especially in a real-time event, of things that are going on and getting information relayed to us, unless we specifically have somebody that sends out, hey, if you have any reports in this area, let us know. If you see that, then feel free to fire away, and we'll probably see that right away. But just in general, Facebook, it's not really too conducive of something for us to follow and to get real-time reports. And going a little bit into kind of all the different hazards to report, we'll go through each of them, tornado, hail, and wind. First, we'll start out with a tornado. And of course, this is kind of your general thing. If you see a tornado, if you see a funnel cloud, if you see a wall cloud, definitely let us know whatever you see out there. One kind of thing I want to kind of urge you guys against, just in kind of certain situations, is to some people, funnel cloud and wall cloud, those are all tornadoes. And try to get people kind of out of the habit of identifying everything as a tornado. So if you're getting ready to call in and report a tornado, first thing I want you to think is, hey, are you sure it's a tornado? Can you see the cloud base and the ground underneath it? Is it connected to the cloud base? Is it in contact with the ground? Is part of the storm is it in the part of the storm where tornadoes develop? Is it rotating? Can you see any debris? These are a lot of questions to ask yourself kind of in the heat of the moment, but generally these are the good things to really kind of check off, before you call in and say, yeah, I got a tornado on the ground. And whenever you do actually describe for us the tornado, make sure that you describe to us exactly what you see and also choose your words wisely. Part of the clear and concise part of being able to give a report. Like for example, I'm gonna back this up a little bit. Over in there in the left, you have that grain silo there in the background, and you have what looks to be kind of a rope tornado extending down behind it. Although, you know, it looks like, yeah, that's more than likely a tornado. You don't necessarily see it connected to the ground. It's obscured by that grain silo. Hey, even if it's obscured by the grain silo, tell us that. You're like, I think it's a tornado, but it's obscured in the background by a tornado. And if, for example, if you report that, we're like, okay, thanks, talk to you later. And then, you know, it moves out from behind it. You definitely see the debris being lofted up, the dirt being kicked up at the surface. Definitely call us back and say, hey, I just called with that report. Yeah, I'm seeing a debris cloud at the surface, dirt being kicked up. It is on the ground. So really, you know, like I said, you know, definitely be as clear, report exactly what you see, and definitely choose really your words wisely. Other things to report was severe thunderstorms. First, hail that's greater than 1 inch. You know, really, I'd argue you report any sort of hail, whether or not you have pea-sized, nickel-sized hail. But definitely, you know, that's pretty much a severe thunderstorm is hail greater than 1 inch. So we'd love to hear from you if you have anything like that. Also, winds 58 miles per hour or greater. And doing a report based off of a wind speed is a little bit tricky. If you have a handheld anemometer, great, stick it up there, get a measurement, let us know how fast it's going. But typically you don't, and you kind of have to estimate. And one thing that we commonly see is overestimation of wind speeds. You know, saying that, oh, it's 70, 80 miles per hour, and then the storm hits a nearby surface station and it's only 40. You know, it's really kind of difficult to gauge how fast is the wind moving, you know, basically by sheer estimation. There's a few people I know of that are wizards with this kind of stuff that actually do get fairly close, but more often than not, we see an overestimation. One thing, having said, you know, hey, winds 58 miles per hour, what to report, damage is also a category of severe thunderstorms. And that's something definitely, if anything gets knocked down by any sort of wind damage, it's definitely something important for you to relay back to us. If you have power lines down, if you have power poles down, you know, definitely send that back. Same thing goes for hail damage. You have windshields blown out, you have siding to houses with holes in them because of wind blown hail. Definitely let us know what you have going on in the area, especially damage wise, because that's really important for A, us making warning decisions, and B, later on, you know, being able to essentially log this in our storm damage archives, just in case, you know, we need to reference anything that's possibly happened in the past. Whenever you're going into hail specifically, whenever you're reporting hail, one of the things that we highly suggest is, you know, try to relay it as much as possible, calling in. If you can't give us exact sizes or exact lengths, you know, call in and give us an inanimate object of, you know, what kind of size the hail is. So up there in the top left, about the size of a bottle cap, you got quarters there in the top right. You have limes down there in the bottom left and golf balls in the bottom right. Relating it to the size of an object makes us a lot easier for us to be able to, you know, concisely put in there, which if you've ever read the warning text, we also include the size of the hail that's falling, and we can identify it as, yeah, this is a spotted or reported event. And then looking at our scale, I mean, pea-sized, dime, nickel, quarter, $half, ping pong, golf ball, lime, you know, all the way up there to grapefruit. If you can, the best that you can, you know, relate back to us, hey, I have this size of hail, you know, try to, if you can't get an exact measurement, try to get us as best as you can close to a common inanimate object, like $half, for example, is kind of falling out of vogue with the less that there is, sorry, I saw somebody put no jelly beans. No jelly beans. Another one, you mentioned jelly beans. Another one that's pretty famous is, you know, marble-sized hail. there are so many different sizes of marbles that, it's really difficult to be able to, we don't know really what to do with marble-sized hail. So if you can go with an object that's not marbles and something that has a consistent size, like your coins or your different kind of ball sizes, that actually works the best for the hail. And see, now you guys are tossing in like popcorn size hail. Anyways, ignoring that, whenever you report hail size, go with like your different kinds of coins, go with your different kinds of balls that are pretty much standard across the entire spectrum for us to be able to quickly, relay that stuff back to the public. If you have a ruler and you do have a very large hailstone, whenever you're measuring the size of the hail, you go across the largest diameter. So for example, for this one, looks like it extends out possibly, yeah, this one's about an inch. Lay it there on the ruler and measure it kind of crosswise to be able to get your measurement to send back to us. And then also for those of you that really like to nerd out on hail sizes, some of you guys carry around calipers to be able to tell us exactly the amount. That's perfect by our book. We appreciate it. Anything really to kind of give us this information so we could be able to send it back as clearly and as concisely as possible to communicate the threat to the public. Anything like this would be great. Next thing with wind damage, really anything, whether or not it's uprooted trees, blown down outbuildings, telephone poles and everything falling down. Really just all of that would be great for us to relay back so we can communicate that, hey, we're seeing wind damage along with this storm. If you're in the path of the storm, please be careful. Whenever you report wind damage, location, where exactly all this happened is very important. The time that it happened, if you happen to watch it happen, great. If you didn't, just be like, yeah, I don't know when it happened. Everything would be great. Description, images, video, all that would be great to send to us. Anything that can give us exactly where it happened and what exactly is damaged is very useful for us as far as relaying hazards on down the line with the particular storm. And so one big thing I want to kind of conclude here, especially with wind damage, if you're not sure what it is or what caused it, don't automatically assume it was a tornado. Don't report it as tornado damage. As I've kind of indicated, more or less most of this talk, especially around tornadoes, is basically how do you not, essentially make sure that it is a tornado. It's a lot of people are very quick to jump to, yes, this is a tornado. It's definitely a tornado that caused it. I have never seen a power line by that. But if you haven't seen it, it's not really that useful to us. And again, whenever we issue warning, it's very important that we're as clear and concise as possible, especially with what's going on at the ground. So, if you're not sure what caused it, that's perfectly fine. Tell us that you're not sure what caused it, just that you have this broken telephone pole right next to, basically on the ground or next to it. Power flashes are another thing to, send us reports about. However, power flashes are one of the ones that, again, it's very commonplace. That's like, oh, I got power flashes, so that must be a tornado. Well, I mean, it's essentially power flashes are an arc from a shorted out power line. It could be damage from wind or ice. You get strong enough wind that you might get the power lines hitting each other and causing a brief arc and pretty much one of those power flashes. And then you might also have an object resting across the live wires, such as tree damage or something like that. I feel like we've all, if you've lived in the Oklahoma area, we all know exactly what I'm talking about with the recent ice storm that passed through. Long story short, definitely report any sort of power flashes that you have, but just don't assume that it immediately means that there's a tornado. It can help us confirm definitely if the environment's good with tornadoes, if we're hearing all these reports with rotation, and then all of a sudden we're starting to hear power flashes near where this rotation's located. It's definitely very helpful at being able to further confirm that there's a tornado present, but especially if, just don't immediately assume that a power flash means that there's a tornado. And so that's pretty much it, all I have for kind of the review of, storm spotting basics. just kind of wanted to give a quick shout out and everything. If you're really interested in kind of severe thunderstorm forecasting, the SPC put together a very nice series of educational videos, kind of pretty much one of the classes that they produce at the University of Oklahoma, where you can go through and learn all the different portions of pretty much storm forecasting and kind of how these storms behave. It goes a lot further in depth than what we kind of are going to go through in this talk. So I'd highly encourage, if you're very interested in this, kind of take a look at this this webpage and kind of peruse around these videos to get a good sense of what's out there and different videos to help further learn more about these storms. And so before we go on, any kind of quick questions going on? Anybody got anything? Like I said, feel free. A lot of you guys have definitely learned your way around the question box. So if you guys have any questions, you can go ahead and fill those in. For now, I'll be switching here with Phil. Phil's going to go into severe weather meteorology, kind of do a little bit more of a dive on how we look at data and kind of just different parts of meteorology to dive into. I'll be here to answer questions, and I guess take it away, Phil.
All right, thank you, Alex. I'm gonna switch over to my screen here. There we go.
Yes.
All right, I can see it now.
Yeah, just tell me next slide and I'll switch it for you.
All right, so as I was saying, what we're gonna do is we're gonna go through some of the forecast tools. So if you have the next slide. So the next slide here, I'm gonna kind of highlight a few things that we look at. So if you hit next, one of the things we look at are upper air maps. So these are maps that are kind of showing us what the upper levels of the atmosphere look like, and this is telling us what's kind of happening above the surface, which drives a lot of our weather. Go ahead and next. Next thing that we like to look at are observed sounding analysis. So this is our skew-T chart. So this is when we launch weather balloons, this is what the raw data looks like, kind of getting a vertical profile of the atmosphere. Next. And the third thing that we use often are mesoanalysis graphics. So these are basically just maps that we look at over kind of a broad region of the size of a few states maybe. And they have several severe parameters that we look at to determine whether the environment is favorable for severe weather or not. Next. So there's really four main ingredients that we focus on when we're trying to determine whether any given day is going to have favorable conditions or unfavorable conditions for supercells, which are our most impactful type of thunderstorm. So starting with moisture. So here in this part of the country, as we mentioned, we're NWS Norman, so we are located in Oklahoma. Our main moisture source is the Gulf of Mexico. So the general pattern that we look for here would be, southerly or southeasterly winds that are going to be pushing that moisture northward out of the Gulf of Mexico and towards our area. Something that we often use to measure the amount of moisture in the air is something called the dew point. So this is basically just the temperature that you would have to cool air to reach saturation. So as you cool air, you begin to saturate it. So eventually you'll reach a point where the air will be fully saturated, you'll have 100% humidity. So the higher your dew point, the more moisture in the air there is. So generally, if we have dew points of 50 to 55, that's enough to get supercells. But really, if we're looking for tornadic supercells, you need those dew points to be much higher, usually greater than 65, but 70 and higher is ideal. Next. So kind of looking at an example of a case from 10 years ago now. This was a big severe weather day in Oklahoma, May 10th, 2010. Next. The moisture source, again, is from the Gulf of Mexico. So you can see those wind barbs there are pointing to the north. So that tells us the wind is coming from the south all across the area, and that's what's helping to bring the moisture northward on this day. Next. So as I mentioned, you want a lot of low-level moisture if you're looking to see if the conditions are going to be favorable for tornadoes. So the reason for that is because that the higher low-level moisture is, the more instability you have in the low levels, and that's going to help support stronger and more persistent updrafts. And we'll see why that's important here in a little bit. As I mentioned as well, southerly and southeasterly winds are the most favorable for bringing that moisture in this part of the country from the Gulf of Mexico. And another thing that we kind of like to see is something called low dew point depressions. So basically the air temperature and the dew point temperature are very close together, and that's going to give you lower cloud bases and a greater chance for tornadoes. Next. So going back to our example from May 9th, May 10th, 2010, we have this southerly wind bringing in a very moist air mass. The temperature at Oklahoma City at this time was 90 degrees with a dew point of 68. And so that yields quite a lot of CAPE, which I'll talk about here in a second, which is basically just a measure of the instability in the atmosphere, because you've got that really hot air, that really moist air, and that combined together gives you very high instability. And on this day, there were several tornadoes reported across central Oklahoma. Next slide. So there's lots of different ways that we monitor moisture. Alex, if you just tap next. So something that we like to use here locally is the Mesonet. The Oklahoma Mesonet is a great resource if you live in Oklahoma for all kinds of different parameters. But we definitely use it for monitoring moisture. This is an SPC, Storm Prediction Center graphic from their website that I already showed earlier, which is a great resource. Here's another view that you can pull down from their website. And again, SKU-Ts, which I'll go through here in a second, which are basically just looking at the data that we collect from our weather balloons. Next slide. All right, so that's one of the 4 ingredients. So we did moisture. So let's go ahead and move on to the next one, which is instability. So starting off with kind of what does it mean when the air mass, often you'll hear about meteorologists, sometimes on the local news or whatever, they'll talk about the air mass is particularly unstable today, or it's stable today, and therefore we are or we are not expecting thunderstorms. So 2 examples here. Alex, if you just hit next. So first example, we have a balloon, and it's sitting in a cool air mass at the surface, and you have warmer air above it. So the question is, will this balloon want to rise or will it want to sink? And the key here is to remember that cold air is more dense, or as you can think of it, as heavier than warmer air. So in this case, if we let that balloon go, it's really just going to sink because it's cooler than the surrounding air around it. So it's heavier. So that air is going to want to sink. It's not going to want to rise. So in this example, when you have cooler air beneath warmer air, that's considered stable. Now, on the other example, if you have the opposite case where you've got a warmer air mass beneath a cooler air mass, and you have that balloon, that same balloon filled with warmer air, and you let it go, it's going to rise. It's going to rise until the air within the balloon is cooler than the air surrounding it. And then it'll either level off or it will sink again. So in this case, the air mass would be considered unstable near the surface because it's warmer than the cooler air above it. All right. Something else that you often hear meteorologists talk about is something called the Cap we'll say, well, the air mass is unstable, but it's capped. So what does that mean? So in this case, you have a warmer layer in between a warm layer at the surface and a cool layer above it. So the warmest layer is right there in the middle. So when you let that balloon go, it's going to hit that layer, and suddenly the balloon will be cooler than the surrounding air around it, and it will stop rising. So if you have that cap basically sitting there low enough in the atmosphere, that's going to prevent clouds from forming, and therefore you're not going to even see storms. So sometimes you can have a very unstable air mass at the surface, but if that cap is sitting there, nothing happens at all. And we call this a clear sky or a blue sky bust. Sometimes when we might predict severe weather because all these other conditions are favorable, but that cap never gets out of the way, and therefore we don't even see storms develop. All right, next slide. So I'm going to go through a little bit about SKUTs. This is something that we spend in school weeks, if not months, trying to wrap our heads around, but I'm just going to give you the basics here. You can definitely do some more looking online for tutorials and whatnot on how to read these, because it can be a lot to look at, but just the basics. Again, this is a vertical profile. So what we're looking at is the bottom of the graph starts at 1,000. Those are units of pressure, so 1,000 millibars. And as you go up, the pressure decreases. So as those units decrease, you're going up in the atmosphere. So as you go up on the graph, you're looking higher and higher in the atmosphere. So the red line here is the temperature of the environment that we measure with our weather balloons. The yellow line here is the temperature of a bubble of air if it was to rise and just cool at the rate that air cools within the normal atmosphere. So air will always cool as it rises. So that yellow line is telling us what the temperature of that theoretical air parcel would be compared to the measured temperature at that same level. And then again, the green line is the dew point temperature that was measured by the weather balloon. And something that we use these very often to assess is the convective available potential energy, or CAPE for short. This is basically how much instability is in the atmosphere. So if you have, again, if your yellow line is far apart from the red line, all that means is that the temperature of that bubble of air is going to be much warmer than the environment around it. So it's going to rise. It's going to want to rise quickly. That's a lot of instability because it's going to want to rise quickly because of that. So basically, the wider the gap between that yellow line and the red line in this case, the more instability we have available to create thunderstorms. And then we also use this to assess if there is going to be a cap on any given day. So you can see there, the red line is again our measured temperature with our weather balloon as it went up in the atmosphere. And if it goes to the left on this graph, that red line, if it goes to the left, that means the temperature is cooling as it rises. And if it goes to the right, that means it's warming as it rises. So you can see there, if you start from the surface, the red line is going to the left, going to the left. It hits a certain point there around 850 millibars, and then it starts going to the right. And so that is the cap. That's the warmer air right there on the sounding. And so when we see that, we think, okay, well, this amount of basically negative energy that's going to help to keep that air bubble from rising is in the atmosphere. And so this has to be eroded before we can see convection freely developing from the surface. And so we call that negative area, that blue area that I had highlighted, we call that SIN, or convective inhibition. All right, so just a little bit more about CAPE. as I mentioned, the further apart those lines are on the graph, the greater the instability is. So the one on the left would be an example of high CAPE. So there's a wide gap there between the environment temperature and the parcel temperature. And on the right, this would be considered a low amount of CAPE. It's kind of a skinny gap, a narrow gap between them. That means that there isn't as much instability available for thunderstorms. So I know that's a lot to kind of wrap your head around looking at this for the first time, but as I mentioned, if you want to learn more, there is a lot online. If you just Google SKU-T, you can find a lot more information about that. So another way that we monitor instability is basically on a weather map, on a 2D map like this one. There's a lot of different types of CAPE that we look at, but this kind of gives us an aerial view, a top-down view of the area to see which parts of the area are most unstable and therefore might have the best chance of seeing severe thunderstorms. So if you hit next. So just to go through a few of these, next again. The first kind of section there is all the different types of CAPE. So there's surface-based CAPE, most unstable CAPE, downdraft CAPE, all these different types, and they all kind of mean something different depending on what you're looking for and what type of severe weather you're trying to assess. So most often we'll use either surface-based CAPE or the mixed layer CAPE. Those are kind of the best for looking at surface-based convection. And most unstable CAPE is often used to look at something like elevated convection. Usually this is what happens. You get elevated convection during the nighttime when the surface is stable. We also use the lifted index. This is basically just the difference between the temperature of the environment and the temperature of the air parcel at a given level. And so the more negative, the bigger the difference between those, the more unstable the air mass is. We also look at lapse rates, and all that a lapse rate is, it's just the change in temperature as you go up in the atmosphere. So the higher your lapse rate, the higher that change in temperature is. And so the greater that change that you have, the more unstable the air mass is. So just to give an example, lapse rates of 7.5 to 8 usually indicate a lot of instability that's sufficient for a severe hail threat. And then LCL, or the lifted condensation level height, that's basically just the cloud base, the height of your cloud base. And again, that's useful for determining tornado threats, as the lower your cloud base is, the easier it's going to be to develop a tornado when you have rotation in your thunderstorm. And then there's a few other fields here at the bottom that we also look at to look at short-term changes. You'll often see, if you ever read discussions either put out by the local office, the forecast discussions, or the mesoscale discussions issued by the Storm Prediction Center, they'll often talk about a lot of these different parameters that I just mentioned within their discussions when they're talking about how unstable or stable the air mass is. All right, so we went through a lot there. We're going to take a short break, and we're going to come back in about 10 minutes. So let's say 7:35 Central Time, we'll come back here and get started.
And there's a lot of you guys that have been asking questions. Unfortunately, I was expected to answer those questions, but now I'm playing slideshow master here. So during this time, we'll go back and answer a few of your questions. All
right, Alex, you ready to get started?
Yep, ready when you are.
All right. Welcome back, everyone. So we are halfway through our 4 severe weather parameters that we like to focus on when we are trying to forecast supercell thunderstorms. So we've already looked at moisture and instability, and the other 2 are lift and wind shear. So let's start with lift. And all that lift is, hit next, Alex, please, is something to give a nudge upward. So sometimes that's all that it really takes for a thunderstorm to develop, given a favorable and unstable environment. Often we need some type of focus to actually lift that air parcel initially to get it to start rising in the atmosphere. So multiple things that we look for that can be a cause of lift. So the first would be fronts, so a cold front shown in blue there, or a warm front shown in red. Both of these are great sources of lift. Something that's very well known to be a source of lift during severe weather events for our area, especially during the springtime, is the dry line. So that's going to separate the dry air on one side from the more moist air on the other side. Outflow boundaries, this usually is lift that is generated when basically cold air with a downdraft from a thunderstorm spreads out along the ground and kind of creates almost like a mini cold front around the storm, and that can be a good source for lift. And then also, if you get enough heating during the daytime, you can get temperatures that are warm enough to really start to lift enough of the air parcels to start to really get convection firing. So starting off with fronts, so we have basically a cross section on the top here of a warm front. And something that it's important to note about a warm front compared to a cold front is that the air rises more gradually along the frontal surface. So you see the cold air mass on the one side of the front on the right and the warmer air mass on the other side of the front on the left. So that slope between the 2 air masses is very gradual. So this leads to kind of slower upward motion, and generally you don't see quite as much stronger convection associated with this because that lift, the lifting mechanism is more gentle. So you can almost think of this, if you had a bowl of water and you took your hand through it kind of at an angle, you're not going to displace as much of that water as if you had your hand, up and down through the water. And as you move across, that's going to create much more movement to that bowl of water. And so that example would actually be something more like a cold front. So the frontal surface is actually more vertical. And so the air rises more abruptly and more rapidly, and that usually lends itself to a narrower area of heavier precipitation and thunderstorms. So another way that we can see lift in the atmosphere is something called convergence. So this is basically just when winds come together. And sometimes in the summertime, this will happen when you get a lot of surface heating from the sun. You'll get some land areas that heat up faster than others, and those create localized areas of warmer air. And remember, warm air likes to rise. So, as that happens, see, Alex hit next, there you go. So as that happens, the warm air rises, and then the air at the surface wants to come in behind it to replace it. This is, convergence at the surface of the winds. And then as those winds converge, that's going to push together more air, and that air has nowhere else to go but up. And so that's going to increase your lift even more. And if you have enough moisture present, then you can get clouds and eventually precipitation to form in this scenario. So this is kind of if you just have the summertime pop-up storms. This is often the mechanism that helps lead to that. As I mentioned before, boundaries are often very important. So in this case, we are looking at a dry line. So you see there on the left, these are the numbers on there. I know they're kind of small, hard to read, but the numbers are the dew points. So remember, the lower dew points show you your dry air mass. The higher dew points show you your more moist air mass. So on the right, we have dew points in the 60s and 70s. On the left, we have dew points in the 20s. And you can see also the wind direction that I've overlaid there on both sides of the dry line. They're almost perpendicular to each other. They're almost pointing directly at each other on each side of the dry line. So that is almost direct convergence along that. And so if you have this type of air mass ahead of the dry line, you can get some really explosive thunderstorm development. And this is what happened on this day here. We had multiple supercells that developed. All right, so as I mentioned, outflow is another example. So you can see here, you've got a thunderstorm in the center, and then if you'll notice, kind of around it, this kind of thin green line to the south of that thunderstorm, that is an outflow boundary. So that's basically created when the cold, cooler air that's cooled by the precipitation in the downdraft hits the ground and spreads out. And we can actually pick that up on radar if we're close enough to the storm. And so you're actually seeing that on this radar image. And so that zone all along the outflow boundary there is something that we look at when we're assessing, when we're watching the radar during an event. That's the area that we're looking at for potential new development of thunderstorms along that boundary, because that's going to lift the air around it up over the boundary and could lead to new thunderstorms. So something that we often use to monitor boundaries would just basically be the measured surface winds. So the mesonet has a lot of different, basically a lot of different stations all across the area. So it's a very dense network. So you can get a good idea of even kind of local changes in the wind direction. And so on this example, there isn't really much of a boundary being shown here. At least not a large scale boundary like a cold front, but this is the type of map that we would look at to kind of pick out those boundaries when they do occur. This is basically just a broader view of a similar thing, but this is from the Storm Prediction Center mesographics, the mesoscale analysis graphics. So this is just plotting the temperature and dew point along with the wind direction. And so you can kind of use all of those to find, okay, where does the wind direction change? And that's where your boundary is going to be. So where can you go to monitor the data? This is another one here. Alex, if you hit next. Okay, actually go back. Yeah, so this is just another one here. What I'm showing here is the surface tab there on the top left. And so if you hit that surface tab, it's going to pull down that menu, and you can look at all these different surface parameters to find where those surface boundaries are. All right, and so the final ingredient, if you remember the 4 ingredients, the final ingredient is going to be wind shear. And so this is important because you need that increasing wind speed or a change of the direction with the wind with height to lead to the rotation that you see in supercells. And then also, you need low-level wind shear to lead to the rotation that's favorable for the formation of tornadoes. And so, Alex, if you just click on this slide, I think it should start to play the video. So here we have an example of wind shear in the atmosphere. So you can see the low-level clouds, the clouds closest to the ground, are moving in one direction, and the clouds above it are moving in a totally different direction. So you can imagine that if you have these kind of 2 different wind directions, that as that changes with height, that's going to lead to rotation in the atmosphere. So if you were to develop a storm with the winds in this example, it's going to start to rotate, basically just based on the environment alone. And so, as I mentioned, wind shear can either be a change in wind speed or direction, and sometimes you have both. So the example number 1 on the left here is basically just increasing winds with height. So the arrows kind of represent the size of the arrow kind of represents the wind speed. So the shorter arrows are light winds, the longer arrows are faster winds. So as you go up with height, you see the wind speed increases. So that is one form of wind shear. Number 2 would be the example of when all the wind speeds are the exact same, but it's just the direction that changes as you go up. And the third example is when you kind of have both, where you have maybe weaker winds at the surface, stronger winds above it, and it's also changing directions. And this third example is what's most favorable for supercell and tornado development. And this is generally what we see on severe weather days. So I'm going to take us back to our beloved SKU-T here, but instead of looking at the temperature and the dew point lines, we're actually looking at the winds on the right. So the weather balloons that we launch also measure wind speed and direction. So the basically the flags, the little triangles on the line, those are 50 knots of wind speed, and the little lines are 10 knots. So you just add it up. So if you had a triangle with 2 lines, 2 long lines, that would be 70 knots of wind. And then the direction is basically just the direction that the wind barb is pointing towards. So Alex, if you hit next, the question that we like to ask to assess whether we will have supercells on any given day is, do the winds change in direction or speed as you move from the bottom of the sounding up to 500 millibars? So in this example, we have weak, mostly southerly winds at the surface, changing to stronger winds as you get closer to the middle of the atmosphere at 500 millibars. So you can see that we went from 15 knots at the surface, and then just above that it goes up to 35 knots, but then by the middle layer there, you've got a triangle and 2 lines or 3 lines, and so that's 70 to 80 knots. So you're going from 15 knots to 70 knots. So that's a pretty big change in wind with height. So that is definitely favorable wind shear. And then second question, we have the wind shear available for supercells. Do we also have the wind shear available for tornadoes? So this is when we're really focusing on just that first mile or even half mile above the surface. So that first little layer, you do see there is that sharp change in speed in the first half mile. We go from 15 knots to 40 knots, just in that small little, half mile change in height. And we also change direction slightly as well. So we have both speed and directional shear. This is another example of a favorable sounding for tornadoes. So kind of putting it all together, we have, Alex, if you hit next here. So yeah, so if we have a wind profile that looks like this, you've got the wind direction at the surface that looks more, kind of into the screen, and then it moves as you go up. So then it's coming from the left to right. So you've got your direction change. The arrow is increasing in size there. So it's kind of designating the change in speed as well. So this is a very, very favorable wind profile. And this type of pattern actually leads to these horizontal rolls basically along the surface. And so if you can get an updraft to form over top of that, this kind of horizontal rotation can then be tilted vertically. And so then you have rotation in the vertical. And so this is kind of how supercells can start to basically, this is the formation process for a tornado. And so Here in this example, you can almost see, if you kind of trace the clouds there, you can almost see the rotation in this supercell, even though it's a still image. It's even tracing it out. That's how much rotation you have in this example. So this was basically just a run through of how wind shear can play a role in supercell development. So kind of summing it up, remember a supercell is defined as having a persistent rotating updraft or mesocyclone, and a mesocyclone, that rotating updraft can help increase your tornado potential, but does not guarantee one. So going back to what I talked about before, if you have the wind shear in the mid levels of the atmosphere, that might be favorable for a supercell. But if you don't have any wind shear down low, it's going to be really hard to sustain that rotation that's going on in the supercell down towards the surface and create any type of tornado. So you kind of need both if you're looking for tornadoes. Some other conditions that are favorable, as I mentioned, again, that high low-level wind shear towards the surface. Usually in the northern hemisphere, if you get surface winds that are more easterly, that's going to be cause a lot of shear, because usually in the northern hemisphere, are at least at these latitudes, the winds in the upper atmosphere are from the west. So if you get easterly winds at the surface, westerly winds above that, that's a lot of shear as you go up from the surface into the middle levels of the atmosphere. We often generally see an increase in shear along boundaries, either frontal boundaries or outflow. And so storms that kind of move along a boundary, that's always a red flag for us when we're watching storms on radar, to kind of give it extra attention and look to see if we can detect any rotation coming out of it. Tornadogenesis, or the formation of a tornado, is more likely if a supercell travels parallel along that boundary, because that's kind of maximizing the amount of time that's going to spend in that high shear environment. And then also, sometimes the storm scale environment might compensate for a lack of larger scale environmental conditions. So and again, this is usually most likely seen along a small outflow boundary, where we might look at the environmental soundings on a given day, and they don't look like there's a ton of low-level shear for a tornado to develop. But if you get an outflow boundary to form and then a storm rides along that, that's going to be an environment that's going to be locally favorable for, potentially favorable for tornadoes. So that's another thing that we like to look at. And another thing that you might hear a lot, either on TV or if you read our discussions, is something called the low-level jet. So this is just a feature that often forms in the plains during the springtime, especially. That's when it's strongest, just above the surface. And so basically it's just a strong tunnel of winds above the surface that can lead to a large difference in wind between right at the surface and just above it. So that's strong low-level shear. So on this example, you can see the winds just above the surface there are 55 or 60 knots. So that's close to 60, 70 miles an hour just above the surface. So that's a big change than probably what is right near the ground. So that big change in speed and direction is what leads to your strong low-level shear. So when we see the low-level jet develop in the springtime, that's usually a good signal that somewhere in that area might have conditions that are favorable given other conditions such as instability and some of the other things that we talked about for tornadoes. So how can you monitor wind shear? Again, going back to the SPC meso analysis, couple different parameters that we look at. So the top there is something called bulk shear, and the effective bulk shear is basically going to be ideal for determining your storm mode. So most often, if you see at least 30 to 35 knots of effective bulk shear, That's usually enough to get supercells. Moving down, the lowest layer of bulk shear, so that surface to 1 kilometer layer, this is the best to look at for determining tornado potential. So if you have values higher than 20 knots, that is a favorable environment for tornado development, given everything else is also favorable. So, you know, this is definitely something that we look at when we're kind of assessing maybe a few days beforehand or even the day of, how favorable is the environment going to be? What is that low level wind shear? And with that, I will pass it off to my colleague Vivek, and he will run through the last portion of our talk.
All right, thank you, Phil. Can you guys see my screen?
Yep, I can see it.
All right. Well, in this section, we will be discussing storm structure evolution, which will build upon Phil's presentation. So as a spotter, you'll encounter a lot of different kinds of storms. Meteorologists who study thunderstorms have tried to classify these storms and label them according to their type. Just about any type of thunderstorm can produce severe weather, but the most dangerous weather often occurs with a supercell thunderstorm. A supercell is a highly organized thunderstorm that is capable of producing a variety of violent weather. As Phil mentioned, supercells form in atmospheric conditions that help them sustain themselves for long periods of time, so their lifetimes may be measured in hours instead of minutes. The most significant tornadoes and the largest hail usually come from supercell storms. So every thunderstorm starts with what is called an updraft. The updraft consists of warm and humid air that rises much like a hot air balloon. The stronger the updraft, the more likely the storm is to produce severe weather. In the most intense storms, the air in an updraft can be over 100 miles an hour. No matter how powerful an updraft may be, rain and hail will eventually move outside the strongest updraft, and gravity will bring the rain-cooled air and precipitation to the ground. This forms the second part of the thunderstorm, the downdraft. A downdraft may bring any combination of rain, hail, and strong winds to the ground. When the downdraft reaches the ground, it has nowhere to go but sideways, so rain-cooled dense air in the downdraft will spread out in all directions. A supercell has an updraft and a downdraft, but what makes a supercell special is its rotating updraft. The rotation in the storm makes the updraft more intense and helps make the storm more persistent and much more organized. So here we see a top view of an idealized supercell with the depiction of the radar, which shows the precipitation location and intensity. The center of the mesocyclone circulation, and where you would most likely expect a tornado to develop, is denoted by the letter T. The leading edge of the rain-cooled downdraft air is denoted by the cold front or gust front. The counterclockwise rotation of the mesocyclone and a smaller scale downdraft on the southwest or west side of the thunderstorm, known as the rear flank downdraft or RFD, produces the hook appearance as precipitation is wrapped around the southwest portion of the circulation. It's important to note that there is a broad spectrum of supercell structures. Supercells are generally grouped into 3 different structure classes, depending on the amount of precipitation contained within the core. Lower precipitation, or LP supercells, are generally dominated by updraft with little precipitation reaching the ground. Classic supercells generate enough precipitation to be able to produce enough downdraft for a moderately strong outflow. And finally, high precipitation, or HP supercells, which are highly efficient precipitation producers and often produce strong downdrafts and outflows. These are the most dangerous when it comes to storm spotting because of the reduced visibility, and if there's a tornado, there's a decent chance it could be rain wrapped. But as a reminder, all supercells are dangerous. HP ones are just more dangerous because it can be difficult to see what's going on. Also, note that in the real atmosphere, it is a continuous spectrum between these 3 types. And now here's the top views of the three types of supercells. Again, for LP supercells, there may be little or no presence of a hook echo, and most of the precipitation is carried well downstream of the updraft. Maximum radar reflectivities in LP supercells are relatively weak, with the maximum values likely produced by a few large dry hailstones. Classic supercells fit the more idealized radar structure that you associate with supercells. These supercells produce the majority of long-lived tornadoes. And finally, HP supercells have large amounts of precipitation that wrap around the mesocyclone, producing a large, high reflectivity hook. Let's talk more in detail about the two different kinds of downdrafts in a supercell. First, let's discuss the forward flank downdraft, or FFD. The FFD is the main region of the downdraft in the forward or leading part of the supercell, where most of the heavy precipitation is falling. It is usually to the east or northeast of the mesocyclone. Sometimes you can have strong outflow winds associated with the forward flank downdraft. When storm spotting, you don't want to be looking through or located in the FFD. The heavy precipitation may obscure the tornado depending on spotter positioning. In other words, it is a dangerous part of the storm to be in due to the reduced visibility, the potential to get hit by large hail, and the risk of getting caught off guard. The other downdraft located in the supercell is the rear flank downdraft, or the RFD. An RFD is a region of dry, subsiding air on the backside and wrapping around a mesocyclone. It is often visible as a clear slot wrapping around the wall cloud. Scattered large precipitation particles of rain and hail at the interface between the clear slot and the wall cloud may show up on radar as a hook or pendant. Thus, the presence of a hook or pendant usually indicates the presence of an RFD. RFDs can have very strong winds in excess of 100 miles per hour and sometimes very large hail as well. The strong winds may cause more significant damage than the tornado itself. Now, an RFD can be wet or dry, or in many cases, a hybrid between the two. When it comes to the development of tornadoes, the temperature and the associated buoyancy, as Phil was talking about, of the RFD has been found to be important to take into account. All things equal, if an RFD is relatively warm, buoyant, and unstable, that supercell would be more favorable to produce a tornado than a supercell with a cold, stable RFD. So here's a diagram from Marquis et al. 2012 that describes the potential importance of the RFD temperature. Again, the research indicates there is an optimal balance at which there is enough cool air to produce low-level rotation, but not so cold to weaken the updraft and thus prevent tornadogenesis. So as a storm spotter observing, an RFD is relatively warm or cool versus very cold is important. The mesocyclone is the defining characteristic of a supercell. It essentially is a vertically oriented rotating updraft. A mesocyclone can often be implied visually by the existence of updraft striations and or curved inflow bands. It usually develops first in the mid levels of the storm and then at low levels under the right conditions. It varies in appearance from barrel shaped to barber pole shaped, and the mesocyclone may not always be visible in high precipitation supercells, which is why it's much more dangerous. So how does the mesocyclone develop? Well, vertically wind shear in the environment creates what we call a horizontal vortex tube. A thunderstorm updraft tilts this vortex tube in the vertical. As the updraft intensifies, the rotating column is stretched, causing it to spin faster. Hence, this is why vertical wind shear is an important ingredient in the development of supercells. Now, let's talk about tornadoes. The latest definition of a tornado is a rapidly rotating column of air extending vertically from the surface to the base of a cumuliform cloud. In other words, a thunderstorm cloud. often with near surface circulating debris or dust when over land, or spray ring when over water. Although its presence is not required, a funnel cloud is often visible and may partly or fully extend from the cloud base to the ground. Note that tornadoes that occur over water are classified as water spouts. Land spouts are actually a subset of tornadoes that occur independent of a parent mesocyclone, and I'll talk more about that later on. As a storm spotter, it's important to understand the storm evolution that leads to the formation of a tornado, or in other words, tornadogenesis. So let's go through the stages for a supercell tornado, starting with the developing stage. First, note that the tornado circulations can develop from either the ground upward or from the middle and low levels downwards. There's still a lot of ongoing research on this topic. In the developing stage, the RFD precipitation southwest of a wall cloud may signal processes that help establish a tornado, such as a developing clear slot. Some tornadic circulations start in the low levels near the cloud base. So if you see rapid accelerations, in other words, increasing and rising inflow of cloud material into an area of tightening rotation, usually beneath the wall cloud, a tornado may be developing soon. The mature stage is potentially the strongest and most dangerous stage of the tornado's lifetime. In this stage, the funnel often has a near vertical orientation. Note that the visible funnel may not extend all the way to the ground or may become hidden inside the wrapping precipitation. Often, the RFD wraps around south and east side of the wall cloud, generally cutting off original inflow air. The rain-free base may take on a horseshoe appearance. The tornado and wall cloud may be found at the north end of this structure. In the dissipating stage, the RFD wraps around the tornado. As a result, the tornado is separating from the warm, buoyant air that it needs for its survival. As this happens, usually the tornado shrinks, tilts, and takes on a contorted, snake-like appearance before finally dissipating. Sometimes this is referred to as the rope stage. It's important to note that although the tornado is not as large as it was in the mature stage, it can still be dangerous. Now, with some supercells, the story doesn't end there. Instead, inflow may be refocused a few miles to the east of the dissipating tornado, and if the environment is favorable, a new mesocyclone and wall cloud will form. The new mesocyclone and wall cloud will become the dominant part of the storm, and a new tornado may form. For safety, you need to always check overhead, often when near the inflow region of a supercell. Situational awareness is important when storm spotting. And you can see on the diagram there, we have the old tornado and now the new tornado. So here's an example of a cyclic supercell in Stockton, Kansas. Note that the old tornado and clear slot in the left of the foreground and new tornado in the right background. All right, so here's an example of a cyclic supercell in Zurich, Kansas. Note there are simultaneous tornadoes from two different mesocyclones. To the left, there's a fully condensed late-stage tornado from an older mesocyclone. To the right, there's a tornado without condensation into the debris cloud, which is becoming better organized in the newer mesocyclone. So what is the current theory on tornadogenesis? First off, I want to emphasize this is still ongoing research. Researchers across the world are still trying to understand why tornadoes develop. I will present a theory on supercell tornadogenesis from Paul Markowski and other collaborators. Dr. Markowski is a professor of meteorology at Penn State. I encourage you to read the cited papers or go to his website for more details. So in step one, we have the development of the rotation aloft. Supercells are storms that have rotating updrafts. Horizontally oriented rotation is present in the supercell environments owing to the variation of horizontal winds with height, known as vertical wind shear. Parcels of air in such a wind field possess what is known as streamwise vorticity. The term refers to the spin that is aligned with the direction the air parcels are traveling. So air parcels that enter the supercell's updraft spin like spiraling footballs. The horizontal spin becomes vertical as parcels are ingested into the updraft, and the collective influence of the spinning parcels results in the mesocyclone or updraft scale rotation about a vertical axis. Updrafts within mesocyclones can be visually stunning, with the updraft being striated and the threads of a screw and the rotation being plainly visible to the naked eye. In step 2, we have the development of rotation next to the ground. Recall that supercell storms typically have an expansive region of downdraft and the outflow that extends from the northeast of the updraft around the updraft's northern flank and wraps around the western flank. Outflow air parcels that are drawn toward the updraft gradually descend as they travel toward the updraft because they're cooler than the environment. Those parcels that travel along the immediate cool side of the gust front experience a horizontal temperature gradient en route, with the warm air to the parcels left and the cool air to the parcels right, with respect to the direction the parcels are. The horizontal temperature gradient generates so-called baroclinic vorticity about a horizontal axis. Generally, a torque is being applied to the parcels by virtue of the fact relatively warm air rises and relatively cool air sinks. So the horizontal spin of the parcels that gradually descend within the downdraft and outflow can become greatly intensified within the sinking airstream and even can be tilted upward near to the surface. Thus, vertical rotation can be acquired next to the ground within the outflow. In the third step, we have the intensification of near-ground rotation. This intensification occurs by the way of the figure skater effect, referred to by scientists as the conservation of angular momentum, or vorticity stretching. A figure skater spins faster as she draws her arms closer to the axis of rotation. This same principle applies to the spin about a vertical axis produced in step 2. If the spinning air can be converged and drawn inward towards its axis of rotation, it will spin faster. One of the principal findings of the Vortex project was the outflow of the tornadic supercells tend to not be as cold as outflow from non-tornadic supercells. In non-tornadic supercells, the downdraft air that bears the rotation that is intensified to tornado strength is sometimes just a few degrees colder than the environment. The suction tends to be strong as well. The combination of only slightly cold air and strong suction from above makes it likely that upward accelerations and convergence near the ground will be sufficiently strong to intensify vertical vorticity toward tornado strength. Conversely, in non-tornadic supercells, the outflow air can be much colder than the environment, which implies that the air is heavy and resists upward acceleration. The suction acting on the near-ground rotation is often weak as well, either because the rotation is shunted away from the strongest suction by the cold outflow or because the suction is just weak overall. The bottom line is that upward accelerations of the cold, heavy air parcels near the ground are inhibited, and air simply spreads away from the storm along the ground. The lack of a strong figure skater effect in this case results in the near-ground rotation remaining well below tornado strength. So there you have the latest thoughts on tornado genesis. So we just discussed supercells. Another storm type that can result in tornadoes are QLCSs. What is a QLCS? Well, it stands for quasi-linear convective system. And essentially this encompasses squall lines and bow echoes. QLCS tornadoes have been in the news the last few years. Here's some recent headlines. May 2nd, 2018, EF1 tornado touches down in Norman. October 9th, 2018, preliminary reports show 8 tornadoes touched down in central Oklahoma. And May 25th, 2019, the room looked like a bomb hit it. 2 killed, dozens injured in a tornado that hit El Reno. So recall supercells have mesocyclones. Well, QLCSs can have mesovortices. QLCS mesovortices can have strengths comparable to mesocyclones associated with supercells. However, they are different than supercells. For that reason, visually, they often look a lot different than supercells. Don't expect to see the same structure. Don't expect to see updraft striations or curved inflow bands, and many times tornadoes will be rain wrapped in these situations. Now, not all mesovortices within QLCSs produce tornadoes. However, the stronger, long-lived, and deeper mesovortices are more likely to produce tornadoes. Also, only about 10% of QLCS tornadoes are rated EF2 or higher. So about 90% of QLCS tornadoes are rated EF0 or EF1, which are considered relatively weak. Of course, if it hits your house, no matter what the rating, it is significant to you. In addition, it's important to take them seriously, as some can be significant. Last year, on May 25th, a QLCS tornado hit El Reno. The tornado was rated EF3. This tornado was only on the ground for 4 minutes, with a path length of about 2.2 miles and a path width of only 75 yards. But there were also 2 fatalities and 19 injuries from the tornado. Here's some photos of the damage from the El Reno tornado. So yes, though it is rare, QLCS tornadoes can be significant and deadly. Again, I want to re-emphasize, they usually look different than supercells. QLCS tornadoes are much more dangerous to storm spot because they are often quick moving, rain wrapped, and usually only last for a little time. So finally, let's talk about other vertically oriented vortices. From extratropical cyclones to suction vortices, the atmosphere is full of vertically oriented vortices at different spatial temporal scales. As scientists, we often try to fit these phenomena into discrete categories, such as tornado. In reality, the atmosphere is a continuous spectrum of phenomena, and the boundaries between these categories may become fuzzy. There are few vortices on the same scale of tornadoes, and sometimes there's ambiguity on how to classify them. We'll talk about 2 of them, landspouts and gustnadoes. In a landspout tornado, the parent cloud does not contain a pre-existing mid-level mesocyclone. They occur due to stretching of the environmental vorticity along a front or boundary, and are often associated with higher base storms. The landspout was named because it looks like a weak Florida Keys waterspout over land. A gustnado is a short-lived, shallow, generally weak, vertically oriented vortex found along a gust front, or in other words, along the outflow from a thunderstorm. Since they're usually detached from the cumulonimbus cloud, they're not considered tornadoes. Gustnadoes are usually visualized by a rotating dust or debris cloud. Remember, anytime you have horizontal winds changing speed, it's not too tough to get some degree of vertical rotation. While they're not considered tornadoes, they still indicate the potential for damaging wind gusts. Here's another example of a gustnado. Here's a video of a gustnado from Balcaster. Note that gustnados are considered a practically ubiquitous aspect of strong convective outflows. Finally, I want to briefly talk about safe positioning. If you are storm spotting in your vehicle, it's important to take account of the storm motion, road network, and other storms. One thing to be aware of is splitting supercells. A left split is more likely to produce very large hail. They rarely produce tornadoes. A right split is more likely to produce tornadoes and may also contain large hail. Splitting storms present a challenge for mobile storm spotting. Left movers are notorious for the massive hail. Right movers may even turn southeast or even southeast. Situational awareness is extremely important. So you can see an example right there. If you're on that pink X right there, get ready for some hail because you are the left split location. If you're in that yellow spot, hail, wind, and zero visibility, that's a very dangerous spot to be in. That's the forward flank downdraft. The red spot, ideally you would think is safe, but it's safe until the storm turns to the right. That storm could start moving south-southeast, and that may not be a safe spot. You got to watch that other storm to the southwest. That may also come in and sneak in from the southwest. So situational awareness is really, really important if you're storm spotting in your vehicle. So I want to end on this most important point. Remember that no report, data, video, or image is worth your life. Safety is always the #1 priority. As you can see from that picture, tornadoes and cars don't mix. So #1 thing is safety is always the most important priority. All right, thanks everybody for listening, especially with some of our technical issues. We'll stay on for a few minutes to answer questions. I will emphasize we may not be able to answer everyone's questions, but we'll try our best. As Alex mentioned, we'll try to get a recording of this presentation up. Also, I know a lot of people are wondering about certificates. We plan to email certificates to everyone. It may take a few days to a week before you get your certificate, but you'll get one via email, whatever email address you registered. It'll be a blank certificate. So if you have multiple people watching, you can print out multiple copies to write everyone's name. Thank you again. Appreciate everyone staying with us, and we'll stay on for a few minutes, till about 8:30 or so. So have a good evening, everyone, and stay safe out there.